Today, we're putting on our detective hats. Our case? A classic physics problem. You know the one, a table, a couple of blocks, a pulley. It might look complicated, but we're going to deconstruct this thing piece by piece and turn this puzzle into a totally solvable mystery.
So here's the scene. You've got a 4-kilogram block just sitting on a nice smooth table. It's tied to a 1.5-kilogram block that's just dangling over the edge. Now, what do you think happens the second we let go? Yeah, it's going to move, for sure. But the real mystery is, how fast? And what are the forces at play? That's the puzzle we're here to crack.
All right, here's our game plan for solving this thing. First, we'll set the scene. Then, we're going to uncover all the forces involved, all the hidden players. After that, we'll pull out our master key, a super important law of physics to solve for the acceleration and the tension in the rope. And finally, we'll use all that info to predict the future.
Okay, like any good investigation, you gotta start with the facts. Before we can solve anything, we need to know exactly what we're dealing with. So let's lay out all the clues for this system right from the start.
So here's what we know straight from the case file. We've got our two masses, M1 and M2. We're told the surface is frictionless, which is a huge clue. And the rope and pulley are ideal. Now that's just a fancy way of saying we're in a perfect physics world for now. So no extra friction or mass to worry about. And super important, everything starts from a dead stop. This perfect scenario lets us see the core physics in action. These are our starting clues.
To figure out how this whole setup moves, we first have to understand why it moves. And that means we need to identify every single force acting on each part of our system. So, let the investigation begin.
And our number one tool for this job is something called a free body diagram. Honestly, think of it like dusting for fingerprints. It lets us zoom in on one object and see all the invisible pushes and pulls acting on it. It's how we're going to make sense of all this.
So let's put our first block, M1, the one on the table, under the microscope. Take a second. What forces do you think are pushing or pulling on this block?
Turns out there are three. First, you've got gravity, obviously, pulling it down. But wait, it's not falling through the table, is it? Nope, that's because the table is pushing back up with what we call the normal force. And then you've got the rope pulling it to the right. That's tension. So up and down, those forces cancel out. The only thing left to make it move sideways is that tension. Okay, time to shift our focus to the other block, M2, the one just hanging out in midair. You can already tell its situation is way different.
For this block, it's a straight-up tug-of-war between just two forces. You've got gravity trying to pull it straight down to the floor, and at the same time, the rope is pulling it up with that same tension force. Now, since we know this block is what's going to drive the whole motion, gravity has to be winning this fight, right?
Okay, we've identified all our forces. We have all our suspects lined up. Now it's time to bring in the law. The one fundamental rule that governs this whole thing. This is our master key, and it's going to crack this case wide open.
And that master key is, of course, Newton's second law. Sigma F equals ma. It's so simple but so powerful. It basically says if you add up all the forces acting on something, that's the net force, it will be exactly equal to that object's mass times its acceleration. This is the golden ticket. It connects the forces we found to the motion we want to find.
So let's apply this law to our two blocks. For block 1 on the table, if we only look at the sideways motion, the only force is tension. So for that one, it's simple. T equals M1 times A. Easy. For block 2, it's that vertical tug of war. The net force is the downward pull of gravity, which is M2G, minus the upward pull of tension. And all of that equals M2 times A. And just like that, we've got ourselves a system of two equations.
And with these two equations, we have everything we need. We are officially ready to crack our first code, the acceleration of the entire system.
This is where the magic happens. We have two things we don't know, A and T, but we also have two equations. The slickest move here is substitution. We know from our first equation that T is just M1 times A, so we can pop that right into the second equation. Then we just do a little bit of algebraic shuffling, get all the A terms on one side, and boom, we're left with this beautiful, clean formula for acceleration.
So now we just plug in the numbers. We use 1.5 kilos for M2, 4.0 for M1, and the good old 9.8 for G, gravity. You run the calculation, and you get your answer. The whole system is going to accelerate at 2.67 meters per second squared. That is our first major breakthrough. The first part of the case is solved.
Now that we know how fast the system is speeding up, finding that tension, the invisible force humming inside the rope is going to be a piece of cake.
Hey, remember that really simple equation we made for block 1? Tension equals mass 1 times acceleration? Well, the hard work is all done. We just have to plug in the acceleration we just found.
So we take our mass of 4.0 kilograms, multiply it by our brand new acceleration of 2.67 meters per second squared, and voila! The tension in that rope is 10.68 newtons. The second part of our puzzle is officially solved.
So we've solved for the forces, we've solved for the acceleration. We basically understand this soul of this system now. And with that knowledge, we can do something really cool. We can predict the future.
So the final question is, how fast is that block on the table moving after exactly 2 seconds have gone by? For this, we can pull out a classic formula from our physics toolkit. The final speed is just whatever speed it started at, which we know was 0, plus its acceleration multiplied by time.
We multiply our acceleration, 2.67 meters per second squared, by those 2.0 seconds, and we get our final answer. After just 2 seconds, that block is already zipping along at 5.34 meters per second. And with that, case closed.
But here's one last thought to leave you with. Our whole solution was built in a perfect world, right? A clean crime scene, we assumed no friction, and a rope and pulley that didn't weigh anything. But what happens if we step into the messy real world? What new forces, what new twists would our investigation have to uncover then? Well, that's a puzzle for another day.